So let's consider the operation of an accelerometer. As you know, this is an ubiquitous sensor, and let's say in typical smartphones we have one accelerometer. In high-end smartphones there are two accelerometers, one for high accuracy, high power, typically for gaming and for, let's say, applications that need a precise information on the acceleration, and one low accuracy, low power, typically for simple things such as, let's say, varying the orientation of the screen and so on. So in practical modern smartphones, there is one single chip which has an accelerometer in 3 dimensions, so a 3D accelerometer, plus a 3D gyroscope, plus a 3D compass, plus a sensor, pressure sensor. So it's called a 10 dimension sensor. But for the moment we can focus on the accelerometer, and just to let's say explain the basic operation, we will consider only a one-dimensional accelerometer, which gives us the acceleration only in one direction. So the basic operation of the accelerometer works according to a set of transducer, because first we want to transduce the acceleration into a displacement. Then we want to transform the displacement into a variation of capacitance, and then we want to transform the variation of capacitance into an electrical signal. Okay. Now we need to, let's say, understand the basic of these transformations, and we consider 1D accelerometer. So we measure the acceleration along one axis. Accelerometer 1D or one axis accelerometer, and we need a mass, then we need a spring, and we need a damping term, some subsystem that provides damping to the oscillations. So the situation is the following. This is a description only in terms of the basic principle of operation, that we will do at how this basic principle of operation is implemented in practical accelerometer. But the situation is the following. This is the mass, and the mass must be connected through a spring with an external case. So this box is the case of the sensor. So the spring has a constant, an elastic constant K, and of course let's assume that movement can only occur along the horizontal direction. So Y is the position of the case with respect to the horizontal axis, and okay, we also need a damping term. So the damping term is some mechanism which damps the oscillation so that it does not continue forever. A mechanical way of representing the damping is with an oil piston, but this is just a symbol. Okay. It's just a classical mechanic analog of a damping system. You have some sort of piston with oil, so that you have to do some work in order to push the piston left and right. This is just a symbol, it's not how the thing is actually done. Typically the damping term can simply be air, because of course in order to move the mass in air you need to do some work, and therefore the oscillations get reduced in amplitude. Okay, let's assume that the relative position of the mass with respect to the case is x. So this is x. So to be more precise, let me change this a little bit. Let me call this 0. So y is the position of the case with respect to the origin, and x is the position of the mass with respect to the case. So the reference system has 0 as the origin, and of course we know that for example, if we consider for simplicity 0 as the position of the mass at rest, so the length of the spring is 0 at rest, we can assume that we have a force acting on the mass which is equal to k times x, which moves the mass pulls the mass towards the left. So what we have, if we write the equation of motion for the mass, we have something like the force acting on the mass is equal to minus kx, and of course the force is equal to the mass times the acceleration, and the acceleration has to be written as x second derivative of x plus the second derivative of y, because the actual position of the mass with respect to the reference system is x plus y. So the acceleration is the second derivative of x plus y. So this is the quantity that we want to measure, the acceleration of the case with respect to the reference system. The case can be the phone, okay, the phone case. So if you so this is the quantity that we want to measure. Okay. Now this is pretty clear, because if you look at this expression, basically we want to measure A, but we can transform A into x, and x is the displacement, so which is the relative position of the mass with respect to the case. And in order to understand why we are transforming the acceleration into x, is we simply write again this expression, but by applying the Laplace transform. So let us do it. if we make the Laplace transform of everything in order to compute the transfer function, we can write something like f is equal to minus kx, which is equal to m times the second derivative of x, which is s squared times x, plus a, which is the Laplace transform of the acceleration. Okay? And of course now we can move these quantities around. I forgot to include the damping term. Let me move back. The damping term is something that is acting in this other direction. When I try to modify, to move the mass, there is a term which goes in the opposite direction with respect to the direction of motion. So I have a force due to damping, Fd, which is equal to a damping term times the velocity. And it goes in the opposite direction with respect to the velocity. So it is this way. So if I want to write the thing completely, I just forgot this piece, sorry. It's simply, let me write it again. F is equal to minus kx minus kx plus minus d x prime, which is equal to m x plus a. This is including the damping term. Okay, if I include the damping, this becomes minus d sx. Let me write it here. It's f is equal to minus kx minus, this is big X, minus d sx. Okay, then I can bring all the terms with x on one side, and I have minus x ms squared plus ds plus k is equal to m times a. And therefore I can write x is equal to minus m a. I can write it here. Over ms squared plus ds plus k. Basically, to simplify everything, one can divide by m, and then one can have something like minus 1 over s squared plus d over m times s plus k over m. So, what do we have here? Basically, we have a transfer function which has no zero and two poles. You have two poles at the denominator. The poles are real because, as you can see, the coefficients are all positive. And why is that important? Because if I have two real poles, sorry, the poles are not real. The poles are with a negative real part. Sorry. So, which means that the system is stable, and the poles are real if the damping term is sufficiently high, because the damping term is the coefficient is in the coefficient of the first degree. So the higher it is, the more real the smaller is the imaginary part, until all the poles are real. And this is the role of the damping term. If I have real poles, what I have is a low pass system. Okay, so that basically at low frequency the displacement is proportional to the acceleration. Okay, this is a low pass system. Low pass filter, which means that the displacement is proportional to the acceleration if the acceleration does not change too fast. Okay? And this is the only thing that we need. So you see, basically, with just a mass and a spring and some damping term, we are able to obtain a transformation of an acceleration, which is something difficult to measure, to a displacement, which is a position which is much easier to measure. Okay? So this is the main part, and once we have this, everything becomes much simpler, because now the displacement must be transformed into a change of capacitance, and this is relatively easy, because if we use this displacement to modify the distance between two plates of a capacitor, we change with the displacement also the capacitance. Okay? So let me write this concept. So at low frequency, this low frequency means smaller than the resonance frequency of the spring. Let's say that then the free oscillation frequency. Spring. The acceleration, the displacement, let's say displacement is proportional to the acceleration. Now we can do the rest, which is transforming the displacement into a variation of capacitance. This is if we do that, we have a capacitive accelerometer, which is the most common situation. So basically what we have is the following thing. We have a capacitor, a parallel plate capacitor. in which one plate is stationary, so it is at a fixed position. We have a stationary plate, and the stationary plate is, let's say, attached to the case. And then we have a moving plate which indeed is attached to the mass. Which means that when the mass is moved, the second plate changes. And in this situation, of course, if we call, for example, d, the distance between the two plates, the capacitance, as you know, is proportional to the inverse of d. So d is the displacement. This d is proportional to the displacement. That x that I've shown you before is connected to this d, and therefore, if we have a displacement, we change d and we change the capacitance. Okay, and in order to do that, we need a very small movement. Typically, the moving parts are extremely have a very small movement because the variation of d, typically the variation of d is something like a few micrometers. Delta d is something like, let's say, 10 micrometers. Okay, so we need a very small movement, but indeed also the distance is small. So a small variation means a variation, a relative variation of the distance, which is not insignificant, and therefore a significant variation of the capacitance. So to summarize this point, basically what we need to do is we have a mass, a spring, and a damping term so that we are able to transform the acceleration into a displacement. Then we use this displacement to move the moving plate of a capacitor so that we can modulate, we can change the capacitance. And therefore we can transform this variation of capacitance into an electrical signal. That is how it is done. How does it work in practice? In practice, this is all done with silicon technology. This mass is a membrane. The typical implementation is that in this mass is done with a membrane. So this is M of silicon oxide, which is obtained with a technique that is called micromachining. Is a technique which uses the typical silicon technology. So this is, let's say, the lateral view. If I look at the top view, I see something like this. I have this rectangular membrane, and then four small, this is the membrane, so this is silicon oxide. And then we have four small connections which connect this membrane to the case. And this is the case. And also the case is silicon oxide. So you see, and the membrane is thicker because you need to have some mass. So this membrane can oscillate in this direction and in this direction. Okay? And these small connections are the springs. So they are the things that you basically have 4 small springs through which the mass is attached to the case. This is the case. So the movement can occur in the vertical direction here, or here in this direction. And actually, the damping term is simply provided by air, because this whole thing is done in air. So basically, if you put the mass into oscillation, at some point, because of attrition with air, the mass stops. Okay. So this is how typically it's done, and this is something that in practice is less than 1 millimeter in both directions, in the X and Y. It's a very small thing. And of course, this is quite simple situation, according to which we are only able to measure the acceleration in one direction. Okay? If we want to measure acceleration along 3 axes, this axis, and the other axis, what typically is done is that the mass is anchored in different way. We have one mass which is anchored to this, which was the case in the 1D accelerometer, but if the accelerometer is in 2D, the case can move in the other direction with respect to an external additional case, which again can move in the other direction. And so we measure 3 things. The capacitances are these ones. Let me just show you this point, and then I will show you a photograph, which I think it's more interesting. No, I just want to separate a bit. Okay, no, never mind. The capacitors are these ones. This is the lateral view. I have the fixed plate on the top and on the bottom. So I change color just to show you that I have a bottom plate here. This is a bottom stationary plate. For the capacitor, and there is also a top stationary plate for the capacitor. So that actually we have a capacitance C1 between these 2 plates, and a capacitance C2 between the bottom part, the bottom surface of the mass, and the bottom stationary plate. And these 2 capacitances are varied when the mass oscillates. For example, if this is D1, the distance between the 2 top plates, and D2 is this one, the distance between the 2 bottom plates, what we have is that C1 is proportional to 1 over D1, C2 is proportional to 1 over D2. If the mass oscillates, C1 is proportional to 1 over d1 minus delta, and C2 is proportional to 1 over d1 plus delta. Okay, and therefore when you have a variation of the mass, both the top and the bottom capacitance change, and this is exactly what we are able to transform into an electrical signal. Let me just stress this fact. C1 minus C2 is proportional to 1 over d1 minus delta minus 1 over d2 minus delta. Let's add some proportionality constant. Let us call, so that it's easier to write, let us call this K1 and K2, two constants, and therefore we can divide in this way: 1 minus delta over d1 plus K2 over d2 plus 1 minus delta over d2. This is plus and this is plus. And here, if we take, if we do in such a way that K1 over d1 is equal to K2 over d2, then we can have that this capacitance difference is equal to K1 over d1 if we do a first order expansion because delta is much smaller than d1. This becomes 1 plus delta over d1 this is a minus, minus 1 plus delta over d2. This goes away, and therefore you see we have that the capacitance difference is proportional to delta. You can write the expression in detail is K1 over d1. Let's not write in detail because I do not have enough space, but you can see that you can put delta you have something which is proportional to delta, which is what we want. We want a capacitance difference which is exactly proportional to the variation of the position of the mass, which is the displacement. I just want to show you the basic concept of the electrical circuit which transforms this capacitance difference into a voltage, and actually is the circuit is a capacitance voltage transducer. Transducer in Italian would be trasduttore. So all transistors are NMOS transistors. You basically have 3 different control voltages, Phi1, Phi2 and Phi3. Okay, just waiting for you to proceed. So this is a switched capacitor circuit, in the sense that the transistors are used only as switches. They are just on or off. They're driven by digital signal, and we have 2 phases. During the first phase, Phi1 is equal to 1, which means it's high, which also means that, of course, Phi1 negated is equal to 0. Then Phi2 is equal to 1, and Phi3 is equal to 0. So in order to understand what happens in the circuit, you have to consider that this Phi 1, 2 and 3 signals go to the gate of NMOS transistors. So when the signal is high, then the transistor is on, which means it's a short circuit, okay? And you can see that when Phi is equal to 1, this node goes to VDD because this transistor is on, and this other transistor is off, and the other transistor that is on is this one. So C1 goes to VDD and C2 goes to ground. So basically the circuit is like this: C1, which is from VDD to this common node, and C2, which is from this common node to ground. C1 and C2 are the 2 capacitances that are changed by the operation of the MEMS accelerometer. The one between the moving plate and the top, between the moving membrane and the top plate is C1, and the one between the moving membrane and the bottom plate is C2. So this is the circuit here. Then this common node goes to the operational amplifier. Then we have seen that phi2 is high, so the negated input is directly connected to the output, like this. And then the capacitance CF is connected to ground because C negated 3 is high. So this is CF. So this is the circuit, basically. And of course, what happens here is that this node, because it's connected to the input of this operational amplifier with feedback, is at virtual ground. And this means that we have the voltage on C1 which becomes VDD, and the voltage on C2 is 0. Okay, that's it. And also, since also the output of the operational amplifier is at 0, is also at virtual ground, also CF is discharged. So also the voltage on CF is 0. That is the situation. So we have C1 charged to VDD, C2 CF at 0. Then we have the second phase. And during the second phase, all the control switches, so phi1 is 0, phi2 is equal to 0, and phi3 is equal to 1. So what happens here is that now C2 is connected to VDD because phi1 negated is equal to 1, and then we have a reversal of the previous situation. C2 is connected to ground. This is the common mode. C1 is connected down to 0. So this is C1. And now what happens is that phi2 is 0, so this MOSFET is off, but phi3 is 1, so this other MOSFET is on, which means that CF is between the negated input and the output. So CF now is in this position, like here, and then of course this is the output of the this one, of the operational amplifier. So now what we have is again the a similar thing to what we had before. This node, you see, is at the input of this operational amplifier, so it is again at virtual ground. Which means that C2 is charged at VDD, okay, and C1 is charged at 0, because the nodes are between virtual ground and ground. So what we need to check now is what happens to the mass, to the charges. Okay, because of course here we had a charge Q1 on the top plate of the capacitance that was equal to C1 times VDD, and of course there was a charge minus Q1 on the bottom plate. Okay, now we have a charge Q2 on the here, just to complete the consideration, the charge coming to this bottom plate minus Q2 is coming from the output of the operational amplifier, okay, because CF is completely discharged. Okay, so the operational amplifier output can provide all the charge that we need. In the second phase, we have C2 at VDD, so there's a charge on the top plate which is Q2 equal to C2 times VDD, and there is a charge minus Q2 here, okay? Now, here we have a charge that is 0, because C1 is completely discharged. But since we had before a charge minus Q1 on C1, where did this charge go? Actually, the only place it could go is on this plate. So on this plate, since the total charge on this node was Q1 before, and now we have minus Q2 here, and the total charge is not changed, it means that we have on this other plate minus Q1 plus Q2. And therefore, on the opposite plate, Q1 minus Q2. Okay? Let me add this consideration. Total charge on node is equal to Q1, exactly as to minus Q1, exactly as before. Why the total charge cannot change? Because you see, this node is floating. It's not connected to a supply voltage. It's only connected to capacitances. So the charge has to go on one of the three capacitances. Okay? And this is exactly what we want, because you see, we have this charge difference. You see, V out, maybe I can just use this consideration, V out, which is essentially the charge on capacitor, the voltage on capacitor CF, because the other electrode of capacitor CF is at virtual ground, is equal to Q1 minus Q2 over CF. But Q1 is C1 VDD, and Q2 is C2 VDD. So we can put VDD out of the equation and have C1 minus C2. So, and this is the transduction that we needed. Of course, we have already seen that this C1 minus Q2 is proportional to the displacement, which in turn is proportional to the acceleration. And therefore, at the end, we have transformed an acceleration into a voltage. This voltage, of course, can be amplified or translated into a digital number and then processed by by any digital circuit. So it's a very so the essence of this capacitance voltage transducer is just to put on a third capacitor a charge which is the difference between the charge accumulated on one capacitor and the charge accumulated on the other capacitor. And these two charges are in turn proportional to the two capacitances, between the voltage applied to the two capacitors is the same in two different phases. Okay? That's it. Okay, so this was just to conclude the description of the MEMS accelerometer. Let me